I'm Dan Smith. I work for Oracle. My role in what I'm talking about today is I work on the specification for JSR 335, which includes default methods. And mostly what you just heard was focused on the language level view of how they work. I want to talk about the VM level view, what's actually changed in the VM spec, and more broadly, the feature set in Java 8 that is relevant for compiler writers and people of that ilk. So I'm curious, how many people here actually work on compilers? Raise your hand. Okay. So I imagine my target audience is people who are going to be targeting Java 8 and want to know about the details of how the platform has changed. I'm not really going to spend much time talking about a nice story about why we do things and how, et cetera. I just want to give you the nuts and bolts of what's new, what you need to know to be able to take advantage of it. Here's my disclaimer. More concisely, this stuff is subject to change, not only because Oracle wants to avoid making promises that they aren't sure they will keep, but because these are features that are being actively developed through the JCP. They've been refined quite a bit, and there's been plenty of work put into them, but still possible that some of the low-level details are going to be tweaked a little bit. So with that disclaimer, here's the set of things I want to talk about. I will focus on default methods for about half of the talk, and then I'll hit some other things, including the Lambda Metafactory, which we use for implementing Lambda expressions, type annotations, and a couple other miscellaneous items. So you got the story about default methods. I won't belabor it here. In Java source, it is possible to now attach code to the method, and the inheritance rules say that that code is the fallback if there's nothing in the class hierarchy. Also, a separate feature but that we just sort of lump in here because it's similar is we've added private methods and static methods in interfaces. So if you are writing a default method, it may be helpful to refactor some of your implementation into a private method, and that's supported. Static methods also, those are sort of motivated by a desire to completely get rid of the garbage classes that were mentioned earlier. Yeah?
Private is not in the source.
Yeah, the private methods are supported at the class file level, but not the source file level.
Thanks. Yes, I forgot that. Okay. So ignore that thing about private methods. It would be nice. It's not supported right now. It is in the VM. And that's the perspective I've been looking at this from.
You said that this is a talk for compiler writers, so we can emit bytecode with
Exactly. So this is my story about why we're even in this space from the Java source perspective. But now let me talk about what the JVM actually has changed. The first part, that's really easy as a spec writer. We just cross out a line that says interface methods cannot be abstract or must be abstract, and now they can have bodies, and code can be attached to them, and everything's great. There's a few little semantic things that we'll have to patch up, but it's deceptively simple to start. Methods in interfaces, along with not having to be abstract, there's a few extra modifiers that we allow on them. And because of the private methods and static methods, invokestatic and invokespecial are updated in the set of valid methods that can be invoked with those instructions. All this applies to version 52 class files, so it's guarded by, if you're in a version 52, then you can use these new pieces of the class file format. Specific details about what flags are supported. The green ones is what has always been allowed in interfaces. and we've added private, static, and strict for floating point. Pretty self-explanatory why you would want each of those. In the case of strict FP, it's because it's really an orthogonal feature to where the method is declared, and so we support it there. The gray ones, you could make an argument that each of them would be nice to have on the method that you have in an interface that has a body. But in each case, we decided that the amount of effort that it would take to get there was getting pretty far outside of the scope of the motivation of why we're here in the first place. So none of those gray modifiers are supported. Maybe in the future, some of them will be. Yeah.
I noticed a bug where like you have a default method and a lambda inside of it. You will have a synthetic method for the lambda, and the modifiers were wrong. They were actually not the ones you see here. So I'm not sure if you're aware of the problem. If you consider a problem of the synthetic methods coming from lambda definitions in default methods.
So you're saying that the Java compiler is outputting methods that have some of these gray modifiers?
Yeah, well, it was actually missing synthetic flag on the
Okay.
body.
Right, okay. Yeah, that's a good, send a message to Lambda Dev about
Yeah,
that.
I wanted to report it back. I couldn't figure out the issue factor.
Right. The email will work to notify somebody about that. Is there another comment? Yeah.
If an interface has a default method which has a body, what is the difference between that interface and abstract class?
Okay, so if interfaces can have these methods, what are abstract classes good for? Is essentially your question. State is the big difference. And there are also these other gray modifiers can be used in classes and can't be used in interfaces. But definitely we're narrowing the gap between the two. Okay, I said that invokespecial and invokestatic are changed a little bit, and this table is meant to illustrate that. So there are two kinds of methods from the perspective of the data structures used by the VM spec. There are method references and interface method references. They're identical except that the interface one, the class being named is an interface. And so we actually need to enhance these instructions so that the interface method ref data structure can be passed into them. You might wonder from a VM design perspective why we even have these two things, because they look the same and there's so much overlap. Does anybody know why that it was designed so that there wasn't just, say, invokvirtual and invokeinterface, the same instruction that took a class method or an interface method? Yeah?
Because of the Java chip stuff, maybe?
I do not know about the Java chip stuff.
Well, there was some ridiculous notion in the beginning that you could have a processor executing bytecode, essentially.
Okay. Uh-huh. Yeah.
There's some extra fields in invokeinterface which were used by the quick bytecode at one point to cap the interface method, I think.
Uh-huh.
It's even worse. Historically, you had the index of you had the itable index in it.
Right, but in the class file, those bytes had to be 0.
Now, yes, but not in Java 1.0.
So there are probably a few motivations. One thing that I settled on looking at it sort of retrospectively, you can optimize the class version a little better because you can, it is possible that C.M is actually inherited from an interface somewhere, but in any case, you can identify exactly where in your vtable, exactly like the slot index that it could end up in, depending on how you implement it. So I think part of the motivation was that invokeinterface is supposed to be this dynamic lookup thing versus invokvirtual being a direct index into the table. But in any case, this is what it looks like, and so we need to add the additional support for interface methods there. That's everything about how the class file format changed. Now let me explain a little bit about how the semantics work differently now that we have these new bits of the class file. This may be a little elementary, I'm not sure. I don't know how much people think about invocation in terms of the way the VM spec presents it. But it's important when thinking about invocations to keep straight. There's 3 different methods that get talked about, or 3 different method names in any case. There's the original reference, like c.m, and resolution is the process that takes this thing and searches up the hierarchy to find an actual method declaration that matches that name and descriptor. Often it is a method declared in C, but that's not always the case because it may be an inherited method. So resolution is the first part. We get a resolved method. And then, in order to get the actual implementation, often this is like the virtual invocation part of the instruction. We'll do another search starting with starting with some class, and again going up the hierarchy, looking for some method that is either the resolved method or something that overrides it. So resolution and selection are 2 steps that are involved in deciding what gets invoked. It might seem odd that if we're doing the selection search, the resolution search kind of seems redundant. But if we didn't do that, then we'd have duck typing essentially. It wouldn't be necessary to have a declaration of the method you're invoking. We'd just match anything that happens to come from the object. And so resolution is essentially there as a sanity check to make sure your class files are consistent. Okay, so what I want to get to is how have resolution and selection changed to account for interface methods that have code. In order to get there, first let me describe this concept of a maximally specific superinterface method. If I have a class or an interface and some method I'm searching for, this just defines how we identify which methods will be considered matches. Of course, it has to be in some superinterface of the class we're talking about. It needs a matching name and descriptor. The third bullet, we're going to exclude private and static methods. So at the language level, these kind of static methods aren't inherited. Private methods in classes aren't inherited, and if we had them in interfaces, they wouldn't be inherited there either. So this search essentially models inheritance, and to avoid a lot of complexity that would come up, we just completely ignore these methods. Then finally, we want to identify the most specific methods out of those that satisfy the first 3 bullets. So let me illustrate. Here's some declarations. I, J, and K are interfaces. Each of them declares a method with the same descriptor. I and J are 2 independent interfaces, and then K extends I. And now I've got 2 classes that I want to search. First, C just implements I and J, and so the maximally specific methods are just going to be the 2 methods. In particular, note that because they're unrelated, I and J are unrelated, so neither I.m nor J.m is considered better than the other. And we're just going to put them both in the set. With D, it extends C and implements K, so we're going to search the superclass C and find I.m and J.m, and then the superinterface K, and we'll find K.m. And now we can note that I.m is redundant because K.m overrides it. So we eliminate that from the set, and the result is just J.m and K.m. the fact that some are abstract and some are default is not relevant to this search. This is just a building block that we use to define resolution and selection. So with that in mind, here's what resolution looks like. And the yellow part is what's new. So I have a method reference t.m, and I want to search t and its supertypes to find the best method the best method declaration that matches that descriptor. We'll try t. We try t's superclasses, and then we'll look at the maximally specific methods in the super interfaces and pick one. And if all of those fail, then it's a no such method error. Note that step 3 is a non-deterministic choice. It doesn't really matter which one we pick. There are actually some corner cases where you can observe what a VM is picking between this set of methods. And that's not new. I haven't highlighted that in yellow. That's the way it's always been specified. So perhaps that is a problem, but it's not a problem we're trying to solve right here. So we continue with the general idea that we'll just pick some interface method that represents the fact that this descriptor exists. And we'll be more careful to make sure it's one of the maximally specific ones. Yes?
If you recompile everything and you don't get any error, in principle there should be only one method, right?
Yeah, so let me go back to these declarations. These are, I was presenting these as class files, as bytecode, but if this is Java source, then class C would have an error in it. So these aren't situations that would come up by compiling Java source consistently. Through separate compilation or through a different language, we could end up there. So anyway, with resolution, if we're in this situation where there's two of them, we just pick one. Then when we get to selection, now we're starting, typically this is like the receivers type. So we start at the very bottom of the class hierarchy. And we do another search. We try S and S's superclasses. At this point previously, we would just give up because there's no implementation of the method. But now interfaces can have implementations because they can have default methods. So we'll look at the maximally specific super interface methods. In this case, what we do with conflicts is we hope to find exactly one non-abstract match. And if that's what we find, great, we select it. Otherwise, there's an error. So if there are two default methods and neither one is better than the other, that's an error. If they're all abstract, of course, that would continue to be an abstract method error. Okay, so that's the key to understanding how the instructions have changed. I'll just go through very quickly what it looks like for each instruction. So invoke interface, we've updated resolution and selection. And so when we resolve an interface method reference, either that's going to find some interface method. It can also resolve to one of the methods in object. And then we'll use that in the selection search. Important here is, as was talked about in the last talk, even in an old class file somewhere that has an invoke interface, this new selection process kicked in. So we can get a default method out of this search without recompiling. Invoke virtual, this slide looks suspiciously similar to the last one. The only difference is the set of things that can be resolved to. So any class method, and in that case nothing's changed because we'll find a class method to invoke. But in the special case in which c.m doesn't exist in the class hierarchy at all and resolution ends up with an interface method, then selection will come back and either match some implementation in one of the subclasses or it will end up matching a default method. Invokestatic is really straightforward. There's no selection that happens at all, so we just resolve the static method, which in the case of a class method ref, nothing happens, nothing is changed. In the new case of an interface method ref, we just resolve it and then it's invoked. And then finally, invokespecial. So there's a few different things that are new here. Invokespecial is kind of a strange instruction. It's mashed together various features. First of all, it's used to invoke init methods. Second, it can be used to invoke a class or interface's own methods directly. Typically, this is to get to private methods. And then it's also used for supercalls to invoke something in a superclass. So what's new is, first of all, interfaces can make use of invokespecial to call their own private methods. And second, besides invoking a method in a superclass, you may want to invoke a method in a superinterface. So the rule is if you use an interface method ref, the interface that is named needs to be a direct superinterface of the caller. So it can only be used to call to point to your immediate superinterfaces. Again, with invokespecial, there's a resolve phase and a select phase. The resolution is exactly the same as we've seen. Selection is a little bit different because we're not doing a virtual invocation. But what we do is, in the case of a class method, the first bullet, if the reference is some ancestor type rather than the direct superclass, we need to search between the direct superclass and the ancestor to find if there's a better method than the one that we resolved to. And that's the effect of the access super flag on classes. For interface methods, we do resolution, and then we'll do the search again. The only difference with selection and resolution in this case is that selection is going to pick a best one. So in the case where there are two and neither one is better, selection will give you an error.
Then when you say current class D implements I, that class D can itself be an interface, right? And it can be a default method that's calling the super.
Yeah, the question is, does current class D include the case of an interface? Yes, I'm being kind of loose with my terminology, but D could be a class or an interface. All right, so that's default methods. What's new is in version 52 class files, interfaces can be interface methods have more flexibility in what they're allowed to have. They can be non-abstract. They can be public or private, instance or static. And then invokestatic and invokespecial can accept some new arguments. And we've updated the resolution and selection to apply the inheritance model to get the new behavior that may be in a default method. Any questions about default methods before I move on to other things? All right. Some of these other items I'm not necessarily the expert on, but I think we have people in the room who can answer just about any questions you might have. So if I give you a blank stare, we'll find the right person. The Lambda Metafactory is an API that we've introduced for the purpose of the Java language being able to support Lambda expressions and method references. So at the site of, say, a Lambda expression, there will be a body that gets compiled into a method. There will be some values that may need to be captured, and there will be an interface that this Lambda expression is meant to encode, like predicate or function or something. Those three things are bundled up with an invoke dynamic call to this Lambda Metafactory library, and then evaluation will produce an object that implements the interface. It uses the method that was passed into it to provide the implementation. and it will store the captured variables. Looks like I skipped a slide. Okay, so here's what the contract looks like, loosely speaking. There are a variety of inputs. In general, there can be a set of interfaces that you want to implement. There can be some captured variables, 0 or more. There can you need a name of the method that's going to be overridden, and then there can be a set of different descriptors for that method. The reason it's a set is because we may have bridge methods with different declarations in super interfaces that have different descriptors. And then we also pass in a descriptor that is the instantiated form of a generic. So let me back up and walk through the example I have going on here. Let's say we want to implement a predicate that is serializable. So I can pass those two types in as the target interfaces. I have a Lambda expression that's capturing a string and an int. And the name of the method in predicate is test. Its signature is object, and it returns a Boolean. Or its descriptor is object, returns a Boolean. The generic version is so that we can have the proper check casts to make sure that the arguments passed in to predicate.test are consistent with what the user expects at the use site. So if I have a predicate on files, I need to do a check cast to ensure that I have a file being passed in as the argument. And then the last one, we need a method handle that points to the actual implementation of this thing. So the compiler generates things like lambda $0. It can also be an existing method somewhere. Any method is fine. Just something that is consistent with the descriptor we expect. So I pass all these things into the Metafactory. It's called the Metafactory because what it gives me back is a factory. There's two stages. So the first stage, I give all the static information and I get a factory back. Then with the factory, I can pass in the captured values, which may be different for each time the code encounters this Lambda expression. And the result of invoking the factory is an object that implements the interfaces I requested. Is that clear? So this is a little more general than just the purposes of what the Java language needs. If there are ways you want to implement 5 different interfaces, that's fine. You just pass in whatever interfaces you want, whatever method descriptors you want, and you'll get back something that satisfies all of those types. Here's the actual code. So it's in Java Lang Invoke. There's a class Lambda Metafactory. There's 2 different methods. This first one is a simplified version. This only has one interface to implement and one method type. And the idea here is this is going to be the very common case. And we want the VM to be able to be tailored to the common case. So we've called it out as a separate method invocation. And whenever the VM sees a call to this method, we want it to be able to recognize that and optimize. So how's the information I mentioned encoded? The name of the method that needs to be overridden is the invoked name. So that would be test in my predicate example. The invoked type is the type of the factory. So that contains both the types of the captured variables and the predicate in this example, the type that I want to get out of it. SAM type is the declared method type. Impl method is going to point to the implementation, and then the last method type is the instantiated generic form that I need in order to do the right check casts. There's also, like I said, another one. This is the alt metafactory, and so it's a little more general. It's a little odd because in order to interface with invoke dynamic and do a variable length of arguments, the required format is for the last parameter to be object ... So that's what we have, and then I have in comments what's actually expected to be passed in through the list of arguments. What's new compared to the previous slide is we have some flags. This is extensible, so in the future, if there's some special case we want to be able to handle that isn't handled yet, and we can add a bit, we can do that and then get some new behavior. And then 2 lists, the extra interfaces that need to be implemented and the extra bridge types that need to be implemented. The counts are just because of the encoding, because we aren't creating arrays, it's just a variable length list. And so that's to convey how many are coming.
Then,
Yeah.
can you go back to the previous slide for a moment?
Sure.
Why is there a difference between invoked, no,
Sorry. Going back. Here we go.
invoked type and sem type?
Yes. So invoked type.
Invoke
Right.
type is the static type of the invoke dynamic call.
Yeah, that is not the.
To do with
the
some logic.
It does have to do with the logic, but it's not the abstract method. The invoked type is the factory type. So let me go back to the previous slide.
The first 3 arguments are automatically generated by invoke dynamic. You can't.
It will include also the
This is the invoke type. It won't have the intersection, but it will include these and that's how we know what interface to implement.
So that's the part that conforms to the bootstrap method signature, basically. Okay.
Dan?
Yeah.
For not for method references, but for desugared lambda bodies, which are private, couldn't you fold the information from the instantiated method type into like inline casts inside the desugared body?
Yes, it's actually, I think for lambdas, my expectation would be that it would be the same types for both the signature of the method handle and the signature of the instantiated method type. So that's there just to support method references where, for example, in the predicate case, if I want a predicate of string but I'm invoking some char sequence method, then I need to encode in the call to the Metafactory that I really need to do a check cast of string.
Otherwise, boxing and unboxing won't work because you can end up in a situation where something takes an object and you don't know which primitive it came from.
Yeah, we had some interesting example. We didn't have this before and realized that's bad news, especially when you mix it with boxing.
Seems like you could align it except for method references.
Yeah, we could have another one that is specialized for only lambdas that wouldn't have that extra thing, or for the case where it's not generic. I'm not sure what exactly the trade-offs would be in that case. So why am I talking about this? Speaking to compiler writers, because you can use it. It's just a library, but the VM ought to be very aware of it, and it's going to be optimized both in terms of its implementation and in what the VM does with it. Java has made a commitment to all of the Lambda expressions are going to be compiled in this way. So in other languages, if it fits how you handle functions or other similar things, then feel free to use it, and you get all the free engineering behind it. Yeah?
So in Java 8, the way Metafactory is implemented is by generating bytecode with ASM and then loading it to a class loader, right?
That's the way it happens to accidentally be implemented in Java 8.
Yeah, that's
There-
why I asked.
yeah.
It's implemented right now this way. So basically the end result when it comes to performance is was as you would generate anonymous class and load it. Like there is no special case in Java 8 JVM to, I don't know, optimize in any way, right?
No, that's not true. In the case, for example, where you're not capturing anything, it only ever instantiates a single instance of that class, and the capture cost is basically free because it gets turned into a constant load when the VM links the invoke dynamic call site to a constant call site. So what you have now is absolutely no worse than inner classes, significantly better in the very common case for non-capturing lambdas, and then there's a whole pipeline of we know how to make this better and faster in the future. So if other languages use this now, you will be guaranteed no worse and possibly better than what you would probably do yourself, and then you pick up all the improvements in the future.
The future could be 8 updates as opposed to waiting for 9.
Yeah.
Do we do the one class per SAM type trick right now?
Not yet.
Okay.
We haven't prototyped that, but we're
Okay.
not shipping it yet.
Also, the performance of Metafactory compared to anonymous class instantiation is something that
Let's discuss it tomorrow.
Lambda forms come in there and play a little part in the performance. Sergey will tell us.
I didn't mention, we're using invoke dynamic, and one of the main reasons is just because it's a convenient way to cache the linkage results. So the first time you encounter a lambda, the factory gets produced, and then after that there's no more execution of the metafactory. And that could be done other ways, but it's convenient to do that with invoke dynamic. Okay, very quickly, a few other new things. Type annotations. The idea here is that types in Java source can be annotated, not just variables, but any type, and in particular even parts of a type. So there are some new targets for annotations, type use and type parameter. And then the idea is you might have a tool that can process these and maybe have its own custom typing rules, something like @not null. So what this means in class files is there are a couple new attributes, runtime visible type annotations and runtime invisible type annotations. These are very similar to what we have right now for annotations. These will get stored on the smallest enclosing class, field, method, or code. And each annotation looks like this. The first 3 fields here are information about how to match up the annotation to the type somewhere in the program. So the first one is sort of like an enum. It tells you what kind of type you're talking about, whether it's a local variable or parameter or whatever. The second one gives you like a path through the program to figure out which where that type lives, and then the third one is a path within the type. So if you have something like a parameterized type, it will say this annotation is attached to the third type argument, for example. So there's all that information, and the last 2 are just like we have with annotations currently. It tells you the name of the annotation and what its element value pairs are. So this is not attached to anywhere the types appear in the class file. Nothing's changed there. This is some auxiliary information. And then what you'll have is whatever tool is processing these things needs to zip them up and take the type annotations and the types and match them up together. Here are a few ways you can access them: JavaX Lang model, JavaX IDE, the ComSun source tree API. All of these provide support for getting at the type annotations. Does Java Lang Reflect have them too? Okay, I didn't know that.
How many reflection APIs does one platform need?
42. So that's it for type annotations. We also have this new feature called repeatable annotations, which is strictly a sugar thing in Java source. There are annotations marked @repeatable, and those annotations can be applied multiple times to the same class or method or whatever. So what the compiler will do is identify those and box them up into a list of some sort with a container annotation type. This doesn't actually impact the VM, but if you're writing a compiler that supports annotations, you probably want to follow the behavior of @repeatable. You must. I don't know how much authority we have to dictate what languages must do, but certainly it would be a good idea. Yeah. What's that?
Why don't we make just all annotations repeatable?
Yeah, I think there were discussions about that. The approach we took here was, this is a pattern that already gets used a lot in like enterprise software. And we wanted to do a minimally invasive thing that would just make it a little easier for them. Certainly there are ways that if we wanted to be more invasive, we could just automatically box them up or something.
So the number of times that an annotation of some type can appear in a given location today can be 0 or 1. 0 if the target doesn't match with 1. So you can imagine wanting to say 2, at least 5, an odd number greater than 5, right? You can imagine all sorts of constraints that enterprise people might have that are completely domain specific, none of which you want to put into anything near java.star. And so opting into being repeatable more than one is actually something that it's good for a programmer to document the intention to do. If in future additional constraints are then sort of designed in, so you might no fewer than 2, for example, because you must provide a min and a constraint one. Anyway, you have a base for expressing that. But it's really, you wouldn't want things to be repeatable sort of by mistake for other source compatibility reasons, which you have been spared here.
There's also kind of pragmatic motivation, which is you have to define container annotation somewhere.
Yeah, I mean, there could be automatically everything is repeatable foo, and then if you wanted, you could provide a different container. There's also some safety in saying, really, these things are meant to be sets in most cases, and we don't want to allow duplicates. All right, very last thing, parameter reflection. So there's a new class file attribute method parameters that just lists all the names of the parameters. It is opt-in. We're not going to automatically put all this in there. There's some reasons for that. You can probably read up more and other things that have been said about it. But I think forcing everyone to commit to their parameter names wasn't seen as a good approach to take. So you can choose to include your parameter names in the class file. Yeah.
So is there a fallback where it reads it out of the debug symbols?
Yes, that's my last bullet here. So if you call get parameter names or get parameters and they haven't been encoded in the class file, you'll just get arg0, arg1.
The answer to that
If
question
they're in the, if it's like Java 5 code and they're in the debug symbols.
Oh, are we going to get to the debug symbols, right?
Yes.
No, I don't think it does that. Is that correct?
The table attribute is not consulted because it's completely optional.
Yeah, then I still have to have the code I have today, except I'll have yet another layer on top where did you opt in? No. Look for the debug symbols? No. Then do some other stuff.
Well, but you can't reflect over the local variable table, not with a standard API. You can do it Erasm.
Oh, sure. I mean, of course I'm using ASM.
I would be surprised if you were assuming the presence of local variable table attributes in production.
I would say you're assuming wrong.
Are they only there for parameter names and other things?
So we have an RPC framework that it does generation at startup time, and it does a bunch of matching rules. And one of the most favored rules by programmers is I want to match my constructor arg names to my
getters, so I can do RPC over them. Otherwise, you end up like repeating gobs and gobs of boilerplate code. So of course I'm doing that.
So there are some other things beyond the parameter names that are stored in this new attribute as well that we've wanted to store for a long time. And it may very well be that you can stop using local variable table for that parameter name purpose and start using this guy instead.
This is a good way to avoid boilerplate for cases like that.
Yeah.
Or for keyword parameters. And there is a Boolean saying, is that the default arg0 you're telling me, or did you really mean arg0?
Okay, so that's everything. Default methods, Lambda Metafactory, type annotations, and then repeatable annotations parameter reflection. Any last questions about any of this stuff?